Hello, my name is Brett. I'm an application engineer with Capture 3D, and today we will be discussing geometric dimension and tolerancing, or GD&T, inside the free GOM software. For those of you that are new or haven't seen our videos before, be sure to give us a like and subscribe for more great content from the Capture 3D team. So GD&T is a powerful inspection function that helps reduce waste and scrap, simplify inspections, and create easy to interpret results due to GD&T's focus on functionality and fit. With GOM Inspect, we now have access to the full breadth of GD&T inspections that take several seconds to fully implement within the software. We will walk through where these tools are located in the software and go through several different examples of applying GD&T functions. So let's get started. For today's video, we are going to be working on a plastic multimedia part using the GOM Inspect Suite 2020 software. Inside this project, we've already imported both our CAD and our mesh data, and a pre-alignment has been applied. We'll begin by going over where and how we can apply GD&T in the software. There's multiple areas in which GD&T can be applied, and we'll start with the easiest, GD&T Quick Creation. Within the software, we are working in the inspection workplace, and the GD&T Quick Creation menu you can find in your workspace toolbar. When you click on it, it will reveal a complete list of all the GD&T inspection elements that we can create. The second location for applying GD&T inspection is in your iInspect. To bring up the iInspect, you can click on the magnifying glass in your workspace toolbar, or you can control right-click anywhere in your 3D view, and it'll appear at the location of your mouse. If you have an element created and selected, say this plane, clicking on the GD&T symbol will drop down inspection related to the element. Finally, the last place to locate GD&T inspection is in the drop-down menu located at the top of the software. Clicking on inspection and then hovering over check GD&T, you'll see a similar menu that we've already seen before, a full list of potential GD&T inspection. Now that we've covered where you can create GD&T inspection, let's move on to creating some. The first and easiest way to apply GD&T to our projects is the GD&T Quick Creation menu. We will start by creating some simple form GD&T callouts that don't require a datum system, such as roundness and flatness. The remaining form inspections would also have similar creation sequence. We'll start by making a CAD exclusive. Left click on the CAD, press the letter E, and it hides everything but the CAD. For roundness, we're going to go to our GD&T Quick Creation and click on roundness. At the bottom of the screen, the software indicates what options we have available to us while this function is active. I can control click, say on this cone. Using the GD&T Quick Creation, we'll construct both the nominal element, apply the appropriate measuring principle, and then prompt us with the roundness inspection where we can apply a tolerance of, let's say, 0.1 millimeters, and then we can create and close by hitting OK. The Quick Creation function is still active, so we could build a few more roundness inspections. Control left click on this cone, hit OK. Control left click on this other cone, and then hit OK. To finish up, I can press the right mouse button or hit escape to cancel. We've checked the roundness. A neat way to visualize roundness of our inspection is to turn on the color representation in the Properties tab. If we click on the roundness labels and then hover on the right hand side, we will reveal double arrows that we can click to show the Properties tab. Or you could press Tab, the hotkey that's default for hiding and revealing the properties. So with the roundness selection, we can go down to our Display tab, click on it, and then toggle Show Color Deviation Representation. I'll untoggle the Show Tolerance Zone / Virtual Condition, and then you can see the colors that are revealed where our roundness is. To better visualize it, I can click on my CAD, hide that by pressing I, and then clicking on my mesh and toggling the visibility. Then, if we wanted to get rid of the nominal elements, say the cone 1, cone 2, and cone 3, we can click on our 3 roundness and then go over to our label on the right hand side, click on label, and then give them a separate label template. We'll switch it to checks. And now that the element and the inspection element no longer share a common label, they'll be separated. Then we can click on all 3 of the cones, press the hotkey I, and then hide them. And lastly, we can change our tolerance legend to plus or minus 550 microns, and we'll be able to scale up or scale down and visually see the areas that are in or out of roundness. Next, we can inspect flatness on the surface and use the same process to visualize the areas that are high and low on our mesh. We'll make the CAD exclusive, and then we will find flatness in our GD&T Quick Creation. We'll click on it, hold down Control, and then hover over a planar area. By left clicking, it'll build the plane and allow me to apply a tolerance. I'll apply a tolerance of 0.2 and then hit OK. The function is still active, so I'll hit Escape to get out of it, and then next I want to visualize this area. By clicking on the Flatness Inspection and pulling up the Properties tab, I can go down to Display, turn on Show Color Deviation Representation, and then turn off the Tolerance Zone. This is built on my mesh, so I'll hide my CAD, and then I'll make my mesh visible. And then we can see the areas that are red and blue based on our legend scaling. To get rid of the nominal planar element, I will click on the Flatness check, press Tab, go to Label, and I'll change the template of my label to checks, which will separate the two, and then I can hide my plane. If I scale the legend to 0.2, we'll get a better area to see where it's high and low on our mesh. We've checked the flatness. Let's make our CAD exclusive, and then we can take a look at creating a datum system and using it for further GD&T inspections. We'll start by creating a simple 3-plane datum structure by clicking on our GD&T Quick Creation dropdown, and at the top, click on Create Datum System. A dialog box pops up asking us to define the elements that we want to use in our datum structure. And we can define our datums on our CAD by clicking the blue icon in the datum line, Create Fitting Element, and then pressing Control and left clicking on the surface that we want our datum. It'll create the elements. I will name this one Datum A. And then we can repeat these steps for Datum B, as well as Datum C. Once we have our datums made, we can create and close and then see the datum system listed in our Explorer tab under Actual Datums. If we had the elements created ahead of time, for instance D1, D2, and A, we would be able to create a datum system from this. I can set datum 1 as plane A, and then I can set datum 2 as a compound structure of D1 and D2. And then I can hit create. For practice, let's create one more datum system, A, B, and then create and close. It's common practice to set up and inspect your datum structure as one of the first steps to laying out an inspection plan. And I want to briefly touch on the ability to use freeform surfaces as a datum structures now. Introduced in 2020 software are freeform datum structures. So for example, if we had this outer contour area as our datum F, we could go and create a datum system and reference that as our datum. And where the datum falls dictates how many degrees of freedom that it constrains. For example, if it is your primary datum, a freeform surface will constrain all 6 degrees of freedom. If it was the second or the tertiary datum, it would constrain the remaining degrees of freedom that are left in your datum structure. We will now move on to applying some orientation GD&T inspections onto our part. The first inspection we will apply is a parallelism check to this inner face of the sliding channel to the opposing face, in this case, datum E. We'll go to our GD&T Quick Creation, click on Parallelism, and then hold down Control and left click on the surface we want. We'll choose our ISO 1101, or we could choose ASME. We will pick ISO. Then the datum system, we can select from our list. It doesn't have to be a particular datum system. You can reference an element, such as just the planar datum E. We select our datum system, we'll apply a tolerance of 0.2, and then we'll create and close. Once this is done, we could continue applying additional parallelism inspections, but that's it for now. Another simple GD&T inspection would be perpendicularity. If we go to the GD&T Quick Creation and click on perpendicularity, we can check the perpendicularity of datum E to datum A, and the most recent slider to datum A as well. If we press down Control and left click on datum E, we can choose our datum system, we'll pick A, and then hit OK. We can repeat this perpendicularity check by holding down Control and left clicking on plane 4. Similarly, I will press and click on datum A, apply a tolerance of 0.2, and hit OK. I'll right click to get out of the perpendicularity creation function, and we've just checked two perpendicularities, datum E and plane 4 to datum A. Now let's take a look at a few more complex inspections. True position with material requirements, composite tolerancing, and surface profiles. We'll start with the true position and the material requirement. If we have an existing feature, say cylinder 1, we can still use the quick creation on it. But first, if we're going to use the MMR, we're going to need to do a linear size check on the cylinder. So I'll go to my Explorer, I'll click on cylinder 1 as well as control clicking on my CAD, pressing E to make them exclusive. And then I'll go to my GD&T Quick Creation, click on Independency Principle, and then finally control left click on my cylinder 1. A box is going to pop up asking me for a tolerance, and I'll set it to just 1 millimeter. And then I'll hit OK. The inspection line that appears on my cylinder label has an upper and a lower limit, defined by the linear point size, the LP. And this is the method the software uses to calculate the size of the cylinder. If I right click and edit the creation of this linear size check, you'll see there's an upper limit, a lower limit, as well as the computation. If I click on the computation method, you can see there's different ways of calculating the upper or the lower limit, say the maximum inscribed or the minimum circumscribed. All depends on the print and the callout. So we'll cancel and leave it as the 2-point size, as that is default correct method. We'll close out of this window, go back to Quick Creation, and then we'll find True Position, or in the software it's called Position. And then we'll control click on the cylinder 1 label, we'll select our datum system, ABC, we'll go change our tolerance region type to circular, and then apply the MMR. It pulls the value from the size check we applied earlier, as you can see. Now let's take a look at what would happen without the material requirement. If I change it to none, you'll see in the box for the check it actually fails, but by applying this MMR, the true position passes. We'll keep the tolerance at 0.2 and then hit OK. It's awesome though to see the MMR effect in real time. Alright, so we've just checked true position on the cylinder by referencing the datum system ABC, and we apply the MMR to this true position callout. Another powerful inspection tool of the software is composite tolerancing. If there were a pattern of holes or cylinders that needed to be inspected simultaneously, say for an assembly fit, we could create an element group of those cylinders, apply a theoretical exact dimension or TED pattern callout, and then apply a composite tolerance to that inspection. And then we could apply both the pattern locating tolerance zone framework as well as the feature related tolerance zone framework. So that way we'd create two TED pattern callouts. The first thing we want to do is have a set of elements that you would need to apply this check to. In this case, I've already created several cylinders that we're going to perform the TED pattern inspection on. Let's take a look at them now. C1 through C7. So to create an element group, we have to highlight all the 7. And then we go up to our inspection drop-down menu and then go down and create element group. And we'll name this one pattern 1. Then create and close. So you'll see now this element group is connected to all of these cylinders. Next, we'll go to our GDT Quick Creation, go down to TED Pattern, and then control click on the label Pattern 1. The creation dialog box pops up, and then we can start filling in the needed areas. I will name this PLTZF for Pattern Locating Tolerance Zone Framework. And I'll set my datum system to ABC, and then my zone type to circular. We won't be applying any material requirement this time. And then I'll click on the composite tolerancing line, toggle use composite tolerancing, apply a tolerance of 0.25, and then create and close. That was our PLTZF. Our next TED pattern inspection will be our feature-related tolerance zone framework that we'll name FRTZF. I'll control click on pattern 1. I'll choose my datum system now to be just AB. Change the tolerance zone to circular. Composite. Click on use composite tolerancing, hit the toggle FRTZF and change the name FRTZF. And then I'll apply a tolerance of 0.2 and then hit create and close. Within our element group pattern 1, we've checked both the PLTZF as well as the FRTZF as indicated by the name within each line. And that's how you can create a composite tolerancing callout. Our last inspection we're going to perform is a surface profile callout. In performing a surface profile callout within the GOM Inspect software, the workflow is very similar to what we've done thus far. Let's make our CAD exclusive and expand our GD&T Quick Creation dropdown. I'll go select on surface profile, and the software is going to prompt me to select an area that I want to build the inspection on. I can hold down Control and click on a patch on the CAD, and after a moment the surface profile check dialog box pops up. And we're going to choose our ISO 1101 and then select our datum system. We don't need to, but I will select ABC. And then I'll apply a tolerance of 2 and then hit OK. And there, we've created a surface profile callout on our part. Say we wanted to inspect more than one patch at a time. How about the opening of this edge? With the surface profile inspection still active, we can hold down Control and Shift, and that's going to allow us to select multiple different patches that it's going to use when it builds the surface profile. And then once we are done selecting all the patches we want, we'll press Control and just left click on a patch. And this will build your surface and allow you to inspect the surface profile. We'll keep the same standard, the ISO 1101, and then choose the datum system we chose before, ABC. We'll keep the tolerance at 2 millimeters. If, say, the print required it, its ability to apply an unequally disposed tolerance zone is at the bottom of this dialog box. If I click on it, I could choose either the ISO or the ASME standard. And if I chose, let's say for example, the ASME standard, you'll see the label be modified to reflect the unequally disposed tolerance zone. We aren't going to use this, so I'll set this back to disabled and then hit OK to create this. And that is how you can create a surface profile along different patches. Lastly, we can visualize the deviations of the surface profile similarly to how we did it on our other inspections. If we click on the surface profile of our label, you'll see it highlighted gray. And we go to the properties by pressing Tab, and on the right hand side we go to display. We'll turn on show color deviation representation. Color might show up, but it's currently hidden by the surface body and by the CAD body. So I'll click on my CAD, press I to turn it invisible. And then I'll click on both the Surface 1 label and Surface 2 label, and I'll go to the display properties and go to transparency. I can toggle this all the way to the right where it hides the surface. Now the colors are visualized. And then I can turn on my mesh and actually see the surface profile on my part. The final thing I would like to cover are the GD&T ISO visualizations. Introduced in the 2020 software version update, we can now change the display of our labels to reflect the appearance on a print. So starting with these surface profiles, if I click on both the surface profile, the surface on both of these inspections, and I'll pull up on the right hand side properties, I'll go to the label tab. If I go to the template, I can see there's different options for toggling the display. If I switch it to ISO, you'll see the label now change in our 3D view. Down at the bottom is ISO symbology that you can edit. You can toggle to not use it. You can have it change to hide the actual values. And then the tendency is the green or red arrow indicating what direction the deviation lies and where it's at relative to where it should be. If you wanted to change the position of these labels, you can edit the annotation plane. If I click on that, it pulls up and allows me to choose which plane it is on. So if I go to the plane and click on plane X, you'll see now it flips to where they're looking in the plane X. And then the reading direction, I can choose, let's say Y. Change your view. We've now modified our label. And then I can hit OK. So let's take a look at some already constructed and laid out labels. Here's an example of roundness that has been applied to our cones at the previous portion of this tutorial. Same with the flatness. That is essentially how you can utilize the ISO visualizations for the labels. If the material covered in this video seems a little daunting, I always recommend utilizing the direct help menu at the top right of our screen. We click on it, type in GD&T, and hit enter. We'll see all the elements related to GD&T. If I click on general information about GD&T, it'll give you an overview of what it is and how the standards are calculated. To have a more generalized overview, I can click on check GD&T and see additional parameters or additional inspections that I can further explore. So say if I wanted to know more on flatness, I can click on flatness, and then we'll see an information such as print, how to find flatness, where it's located in the software, the symbols to click on, and then we can scroll down and it provides a further explanation of what flatness is and how it's calculated. It's a very useful tool for those that want to get more information. That is the direct help menu.
So that concludes our video on GD&T inside the GOM Inspect software. And we have covered quite a range of capabilities, and GOM has done a tremendous job of making the functions quick to use and very user-friendly. And with the full suite of GD&T functionalities, GOM Inspect will allow anybody to perform quick analysis of their parts, from your basic cylindricity callouts to your full composite tolerancing of a hole pattern. And this is just one of the many uses for GOM Inspect. To see other applications and functionalities of the software, be sure to check out our other videos. And with a like and subscribe, you'll be the first to see anything new and upcoming. So thanks for watching.